So we are on our last section for stats, and I'm combining correlation and regression. Your homework is going to rely more on understanding of correlation. You just have one shorter assignment for regression. I am going to have two videos this week. The first is this one, focused on correlation. The second one is going to give you some understanding of regression, and then I'm going to go over the correlation activity homework in the second video. So let's get started. I have some goals for you this week. The first is we're going to understand what the Pearson correlation is. There's different types of correlations. We're going to focus on the Pearson. We're going to learn how to interpret it, things we should and shouldn't do in interpreting it. And then part two is going to be stuff that connects to the regression. A correlation, you can talk about things in terms of a correlational design when I'm interested in looking at relationships between two variables, hours of sleep and marital satisfaction, hours of studied and my test scores. It also can be used as a statistic, and that's what we're going to be focused on. And there's different types of correlations out there. We're going to focus on the Pearson. You would need to know the type of data you have, the nominal ordinal interval to make a distinction which statistic you would want to calculate if you were interested in looking at relationships between two variables, which is most often you would then run a correlation. So I've got this general data that looks at two different variables that are So for Pearson, we need to have two variables. I've got family income and I've got students' grade average. For each participant, so you've got this column of person as this row, then my variable 1 is income, my variable 2 is average grade, and then I've plotted each one of these points here. So this person right here is this last person N, all right? And then this first person here is this person A, and this is made up data. What you're seeing here, this graph you're seeing here, we call Scatterplot. It helps you in a picture see your data. So we see we have a linear trend, which is an important part of a correlation. You can kind of visualize a line right there. You can also see that it is a positive relationship. So correlations, we're going to use descriptors in terms of strength and sign being positive correlation or negative correlation. Okay, so let's learn a little bit more about this. It is a linear relationship. Your book gives you the example of hours slept and happiness. So again, two variables. How happy are you on a scale of 1 to 10? How many hours of sleep did you get? So both of those are This, again, is the scatter plot that goes with this data here. Again, I could say that this is a linear relationship because I can kind of see a line through those dots. I also am going to say it's a positive correlation. Again, we're going to talk a little bit more about that. So when I look at my scatter plots, it's a way for me to easily identify what kind of relationship I have before I calculate that R. It also will help me identify outliers. Outliers are not good things that we want in a correlation. It will disrupt your correlation calculation value. Although you're not calculating it, when it gets calculated, it gets really messed up with outliers. We'll talk over that in a minute as well. So positive correlation. Positive correlation means both increase or both decrease. So you can see which graph do you think is the positive? Give you a hint. It's the one with the positive underneath. This guy right here is positive. Negative correlation is our other side. Positive correlation, you're going to have an R greater than 0. Negative correlation, you're going to have an R less than 0. Negative correlation means a mismatch. As one goes up, the other goes down. So as I consume more hot coffee, I have lower temperatures. When I consume less coffee, I have hotter temperatures. That's what that graph is saying there. When we do correlations, again, it is important it has a linear relationship. All of these in this example here all have linear relationships, though some are going to have a weaker correlation, a score that's closer to 0. So look across these four and think about which one would probably give you a score closer to 0. That's going to be where the dots are the most dispersed. Now they're dispersed, but they're not, you could still say, well, I can't see a line in there, but I can't see any other shape. So that is okay. All right, so which one of these would give me the strongest correlation? That would be the first question. Which one is going to give me the weakest correlation? That would be the second question. First question, this guy, A. A is going to give me the strongest. Anytime you see a straight line with the scatter plot, it means that's awesome. Both of them really related to each other, strongly related. Our weakest one, I'm going to say, is B. Those dots are the most spread out. Although D has a lot of spread out dots, you still have more dispersion with B. All right, so when I said I can see dispersion, I can't see any other thing, that's going to be okay. If I run a scatter plot and I have something like this, ooh, that's like a N shape. That's bad. Cannot run a Pearson with that, okay? All right, so Pearson is the one we're working with. It's data, and I need to kind of see a line or a lot of dispersion where I don't see any other thing besides a line. So I don't want a U, I don't want an M, I want to see dispersion, or I want to see some sort of line. When I calculate an R, you're going to get a value between -1 and 1. -1, perfect negative correlation. 1, perfect positive correlation. Both of those are awesome. When we talk about strength of a correlation, it is going to be, regardless of the sign, is that value close to 1 or -1? The larger the correlation, ignore the sign, the stronger the correlation. Sign is going to help me how to interpret those correlations. So a positive correlation, I can say both increase, both decrease. Again, positive, think of positive being a match. Negative, as one goes up, the other goes down, or vice versa. Again, we are running what is known as a correlation coefficient, and the one we'd be running and focused on right now is Pearson. When we talk about interpreting, you'll see, depending on the way you measure things, you can say that there's a positive correlation between study time and test scores. Well, I can say the same kind of finding, but if I've measured it differently, I might have described it as a negative correlation. So if I looked at questions wrong instead of test score, that same data you're going to see as a negative correlation because I spend less time studying, all right? I'm going to get more questions wrong. That is the same kind of idea, but studied in a different way when I look at the less time you study, the lower your test score, or the more you study, the greater your test score. All right, so it's important to make that distinction. When you're going through and doing a literature review, don't superficially look at, oh, well, one had a positive and one had a negative. Well, those both could say the same story, just that they measure things a little bit differently. Okay, so this is an extra credit question for your homework. You'll see homework EC1. You're going to tell me A, B, or C, or D and read that question. Other types of correlations you can do is a Pearson. Pearson is if you have two ordinal data rank order. All right, so if you've got rank order data and you're interested in relationships, you would run a Spearman. If you have two nominal data, you would run a chi-square. A chi-square does talk about relationships. Chi-square is the next chapter, which we're unable to get to for this semester in spring 20. But it is another way of looking at relationships. If you had one variable that was nominal and it was like a yes or no, boy, girl, just two categories, and then your second category was data, you would run something called a point biserial correlation. So again, there's different types of correlations. The only other correlations you should know, you really need to know about Pearson, but the second guy might be just one loose multiple choice question. Spearman, two ordinal Spearman. Interpret in the same way with the -1 and 1. When we look at a correlation again, strength is all about the number. Ignore the sign, look at the number. When we look at a correlation, even though it's got that -1 to 1, it's not a proportion. Don't interpret it like a proportion. Don't talk to it like a proportion. When we talk about correlation and we're interested in strength, we're going to do something called R squared. R squared is literally your correlation squared, R times R. So if I had calculated correlation, I got a correlation of 0.6, and I was interested in R squared, which I also can call the coefficient of determination. I'll use both of those interchangeably. On a test or exam, I'll say coefficient of determination / R squared. And again, if you have R, you literally square it. So my R squared is 36.36. And how would I interpret that? R squared is like eta squared. All right, it is, in terms of a correlation, we would interpret it as the proportion of shared variance. So if I had an R of 0.5, my proportion of shared variance, or my coefficient of determination, is 0.25, 0.5 times 0.5. If I had an R of 1 and I had an R squared, it would be 1. 1 times 1 is 1. That is 100% shared variance. If I had an R squared of 0, of course, they have no shared variance. So those are going through and giving you that. This also can be interpreted in terms of a predictor relationship. So a predictor is when one of your variables is used to predict the other, and that's going to be our next step, and that's going to be discussed when we talk about regression in video 2. When we talk about correlation, this is how you'd see it reported, R parentheses. That parentheses number is going to be degrees of freedom. And then you see the R value, and then you see if it's significant or not. The significance, again, is based on sample size. Sample size is going to help determine is it significant or not. If I had a R squared of 0.54 and I only had 4 people, might not be significant. If I had an R squared of 0.54 and I had 100 people, likely significant. So again, sample size plays into that. Sometimes when I'm collecting data, I'm going to have multiple measures I'm interested in seeing relationships between, and we call that a correlation matrix. And so that's when you go through and you're seeing a bunch of different relationships. So here's an example of a correlation matrix. So again, this is taken from your book, but this first number is showing what is the correlation between temperature and panting. Then what is the correlation between stretching and temperature? What is the correlation between wing venting and temperature? What is the correlation between yawning and temperature? When you see these stars, those stars indicate, as indicated here, those are significant. This is called a correlation matrix. In a correlation matrix, you only see the numbers on one side because actually they would be duplicated over here if you ran it. So we don't want to duplicate it. It's the same. So this number here would be right here, temperature and panting, and I don't need to duplicate it because I only need to see that relationship one time. These dashes are temperature correlated with temperature would be 1. We don't need to know that. That's not informative. It's the same number with the same number. So that's your correlation matrix, which is really informative when you're trying to look at multiple things, how multiple variables are related. All right, so we have some possible things that we need to discuss when we talk about correlations and interpreting them. One, correlation is not causation. Cannot say cause and effect with this, right? Even if you have a predictor relationship, do not say cause and effect. Cause and effect only for experimental design, okay? Another thing we need to consider is statistical significance. All because it's statistically significant, is it real? Is it significant in real life? Is it something I care about? So if I had samples and I was collecting 1,000 people, I might see a lot of significant correlations. I then need to ask myself, is that relevant? Is that important? All right, so that's one thing to think. Another thing to consider is when you're running correlations, sometimes people are only looking at one subset of their data. We call that restriction of range. That is a no-no. You do not do that with correlation. And then another thing, of course, to consider is if I've got the N or the U in my data, that curve linearity, again, non-linear is another way of saying that, then I'd want to run my Pearson, which I had already discussed. So correlation is not causation. We don't know which direction it is. We also don't know if it's a third variable. Example of this. Does number of churches predict crime? No, both of those are related to populations. More populations, you have more crime. More populations, you have more churches. It's a third variable. This example, restriction of range, again, some researchers could be only interested in upper performers, people who had the higher X value. Can't do that. You need to look at all of it. And then again, outliers is another thing that's important to consider. Outliers throw your data off. Look at the two here. All right, when you've got the outlier, when you don't, it can throw your data off. You don't want outliers. All right, so we talked about our correlation matrix. Again, you're going to need to carry on